Saijayani Academy. In this video, I am going to solve 2019 Dcet question paper of Civil Engineering version code A. So, from branch Civil Engineering question paper series A, we will solve Dcet 2019 question paper. In this question paper, I am going to solve the questions on Unit 3, that is Engineering Mechanics and Strength of Material, which is for 14 marks. So, in Unit 3, very first question, the question number 97, the system of force in which line of action of all forces act at a point is called option A, concurrent, option B, coplanar, option C, non-concurrent, option D, non-coplanar. So the question is about engineering mechanics. So in engineering mechanics, we have studied the system of forces. So the system of forces. So we mainly have three systems of forces, which are parallel forces, concurrent forces, and coplanar forces. Coplanar forces, again we have non-parallel, non-concurrent, and non-coplanar. So these are the main types of system of forces. So first one, parallel forces. What are parallel forces? If a system of force having many number of forces which are parallel to each other are called parallel forces. So I will consider force F1, next force F2 and force F3, which are parallel to each other. So if forces are parallel to each other, then they are called as parallel forces. If they are acting same directions, they are known as like parallel forces. If they are acting opposite direction, then they are known as unlike parallel forces. Next, non-parallel forces. Which are non-parallel forces? If a system of forces having many forces which are not parallel to each other, that type of force are called non-parallel forces. Consider F1 and consider F2. So these two forces are not parallel to each other. So these type of force are called non-parallel forces. Next, concurrent forces. So what are concurrent forces? If a system of forces consists many forces whose point of action act at one point are called concurrent forces. Consider there are many forces such as F1, F2, F1, F2, F3, F4 and F5. So there are 5 forces acting at one point, acting at a same point, or the line of action of all forces acting at a single point. These type forces are called concurrent forces. Next, what are non-concurrent forces? If a system of forces consists many forces whose line of action does not act at a point, then they are called the non-concurrent forces, such as F1, F2, F3, F4, whose line of actions does not contact at a same point. So these type of forces are called non-concurrent forces. So a system of forces in which the line of action of all forces does not act at a single point, that type of force are called non-concurrent forces. Next, coplanar forces. Coplanar forces. non-parallel forces is a non-concurrent forces. So first one parallel forces, second one concurrent forces, fourth one non-parallel forces, fifth one non-concurrent forces. So third one, what are coplanar forces? If a system of forces acting on the same plane, then they are known as coplanar forces. So these are four forces acting on the same plane, then they are known as coplanar forces. Then what are non-coplanar forces? If a system of forces which are not acting on the same plane, then they are known as coplanar forces. So consider this is a one plane on which force F1 is acting and another plane on which force F2 is acting. So here the forces are acting on different planes, are not acting on the same plane. Then these type of forces are called non-coplanar forces. So parallel forces, if two forces are parallel to each other, then they are known as parallel forces. If two forces are not parallel to each other, then they are called non-parallel forces. If all the forces acting at the same point, or the line of action of all forces acting at the same point, then they are known as concurrent forces. If the line of action of all forces are not acting at the same point, then they are known as non-concurrent forces. If the forces acting on the same plane, then they are known as coplanar forces. If the forces are acting at different planes, or if the forces are not acting at the same plane, then they are known as non-coplanar forces. So, but in this question, the system of forces in which line of action of all forces acting at a point is called concurrent forces. So, in this system of forces, the line of action of all forces acting at a same point. So, option 2, concurrent forces, is belonging to this question. So, right option is option A, concurrent forces is the right answer. So, next question, question number 98. The moment of inertia of a triangular section of base B and height h about the axis passing through the center of gravity and the parallel to base is given by option A, bh cube by 4, option B, bh cube by 8, option C, bh cube by 12, option D, bh cube divided by 36. So, the moment of inertia of a triangular section, the moment of inertia of a triangular section of base B, so base is B and height h. So height is h. Height h about the axis through center of gravity. So about the center of gravity and parallel to the base. So parallel to base. We know that the center of gravity for a triangular sections lie at a distance 1/3 of its height from 1/3 times of its height from base and 2/3 of its height from its apex. So it's apex and it's a base. So the center of gravity CG will always occur at a point 1/3 of its height from its base and 2/3 of its height from apex. So the center of gravity of a triangular sections always acts at a point from 1/3 of its height from its base. So we know that the moment of inertia of triangular section about its base is equal to bh cube by 12. So the moment of inertia of a triangular section about its base is given by bh cube by 12. But he is asking the moment of inertia of a triangular section of base B and height h about the axis passing through center of gravity and parallel to base. He is asking parallel to base. So for this question, from parallel axis theorem, we know that I moment of inertia of a triangular section about base is equal to Ig plus A y bar square. So this is the statement of parallel axis theorem, where the moment of inertia of a triangular section about base is equal to moment of inertia of a triangular section passing through the center of gravity and parallel to the base plus area into the distance between the center of gravity and base. So where Ig is the center of gravity parallel to base, and y bar is distance between CG and base, that is y bar is equal to 1/3 of its height. So I want to find Ig, so Ig become, so I base minus A y bar square. So area A is equal to half into B into H. For a triangular section, the area is given by half into B into H, and y bar is equal to 1/3 of H. So by putting this value, Ig is equal to, we know the moment of inertia about base, BH cube divided by 12 minus area half into base into height into 1/3. It's 1/3 of H whole square. So we will get BH cube divided by 12 minus H square into H, BH cube. So 3 squares are 9, 9 twos are 18. So on simplification, 18 BH cube minus 12 BH cube divided by 206. So 206. So 18 minus 12, it's 6 BH cube divided by 206. So 6 ones are 636. So BH cube divided by 36 is the answer. So the moment of inertia of a triangular section of base B and height H about the axis passing through center of gravity and parallel to base is given by BH cube by 36. So Ig is equal to BH cube by 36. So this is the right answer. So among the option D, BH cube by 36 is the right answer. So don't get confused. So by looking this option C, BH cube, it seems option C is the right answer, but it is the center of gravity of a triangular section about the base. But he is asking passing through the center of gravity and parallel to its base. Then the moment of inertia become BH cube by 36. It is a very important concept. So next, question number 99. The stress in a body, if suddenly loaded, is dash the stress induced when same load is applied gradually. Option A, 1/2. Option B, equal to. Option C, twice. Option D, 4 times. So we know that stress for a gradually applied load, stress for gradually applied load as sigma is equal to P by A. So stress for gradually applied load is given by the ratio P by A, where P is the load and A is the area. So P in Newton, area in meter square. So stress for gradually applied load is given by P by A. Stress for suddenly applied load, so sigma is given by 2 times of P by A. So 2 times of its load and area. So for suddenly applied load, stress is always 2 times of the stress when gradually applied load. So I will consider a component on which load is applied gradually. So then the stress is produced. If the same component is subjected to sudden load or suddenly applied load, then the stress produced in the suddenly applied load is always 2 times greater than the stress produced in the component when gradually load applied. So the stress in a body, if suddenly load is applied, dash stress induced when the same load is applied gradually. So option C, twice is the right answer. So the stress produced in a body subjected to suddenly applied load is twice the same body when applied with a gradually applied load. So option C, twice is the right answer. So next question number 100. The maximum shear stress induced in a body dash times the average shear stress in a rectangular section. Options are option A 1, option B 1.5, option C 2, option D 1.5. So the maximum shear stress induced in a body dash times the average shear stress in a rectangular section. So he is asking what is the value of shear stress which is greater than average shear stress in case of a rectangular component. So I will consider a rectangular component of width B and depth D. So consider the side view of the rectangular component of a section of width B and depth D. Here I consider a small element on a side cross section of that rectangular component. So the neutral axis always lie at its center. So the distance between the neutral axis and outermost fiber is d by 2. It's a half of depth. And so the distance between the center of gravity of small elemental component and the neutral axis is y bar. The distance between the center of gravity of a small element and the neutral axis is y bar. So the distance between the neutral axis and the small elemental component is y. So the depth of small elemental component is given by d2 minus y. So the distance is d by 2 minus y. By subtracting d by 2 y in d by 2 we will get the distance of a small elemental component. So B is the width, d by 2 minus y is the depth of the small elemental component. So we know that shear stress is given by F into A into Y bar by I into P, where F is the applied force which causes shear of a component, B is the width, D is the depth, A is the area, I is the moment of inertia, and Y bar is the distance between the neutral axis and the center of gravity of a small elemental component. So Y bar, from Y bar we can write Y bar is given by Y plus half of this small element, half of this small element depth is given by d by 2 minus y. On solving we will get 1 by 2 of y plus d by 2. The y bar value is 1 by 2 inside the bracket y plus d by 2. So what is the area of small component? B into d by 2 minus y. So area of small element. So we know that moment of inertia is given by BDQ by 12 for a rectangular section. By putting these values in this equation, we will get this. So F into B, d by 2 minus y into half of y plus d by 2, b into d by 2 minus y into b divided by 12. On solving, we will get 6 times of F d square by 4 minus y square BDQ. The shear stress is maximum when y value is 0. So what is y? The distance between the neutral axis and the outermost fiber of the small elemental component. So if y is 0, then shear stress becomes maximum. Then put the value of 0 in place of y. We will get tau is equal to tau become tau maximum 6f 4 times of b into d. 6 by 4 f by b into d. We know that b into d for a rectangular section B and D is an area. So force by area means again it's the stress or shear stress. So 6 by 4 means 1.5. So tau maximum is 1.5 times of T average. So the right answer is option B, 1.5. So the maximum shear stress induced in a body is 1.5 times of the shear stress in a rectangular section. So option B is the right answer. So next question number 101. In case of composite section having 2 or more bars of different length, then the change in length in each bar is option A equal, option B bar does not undergo any deformation, option C not equal, option D none of these. So in case of a composite section having 2 or more bars of different length, so a composite section having 2 or more bars with different length. Consider 3 bars of different length when it is subjected to a load P. So this is bar 1, bar 2, bar 3, which is a composite section having 3 bars of different length. So this is L3, length of bar 3, this is length 1, this is length 2, L2. So the question is, in case of composite section having 2 or more bar of different length, then the change in length in each bar is. So bar 1 has one length, bar 2 has other length, bar 3 is other length. So 3 bar have 3 different lengths. When it is subjected to a load, what is the deformation in each bar? So we know that the strain produced the strain produced in a composite section is equal in each bar. So the strain produced in a composite section is equal in each bar, which means the total strain is denoted by small letter E, strain. The total strain produced in composite section is equal to strain in bar 1, strain in bar 2, strain in bar 3. So what is strain? Strain is defined as the deformation per unit length. So change in length divided by original length is equal to change in length of bar 1 to original length of bar 1, change in length in bar 2 to original length of bar 2, change in length of bar 3 to original length. So from this equation we can say that the strain produced in each bar is same, so the deformation produced in each bar is also same. So the right answer is equal. Option A, equal. So in case of composite section having two or more bars of different length, then the changing length in each bar is equal. So option A, equal, is the right answer. So next question number 1 or 2. The point of contraflexure is a point where option A, maximum bending moment occurs, option B, zero shear force occurs, option C, maximum shear force occurs, option D, zero bending moment occurs. So point of contraflexures. So what is the meaning of point of contraflexure? So in case of overhanging beams, we will get a point of contraflexure, which means the point where the bending moment changes its sign is known as the point of contraflexure. So consider a overhanging beam. Consider a overhanging beam subjected to point load. Consider a overhanging beam which is subjected to point load at its free end. So it is a overhanging beam, A, B are the support and W is a point load acting at its free end. Then the shear force diagram becomes, so this is the shear force diagram. So positive shear force diagram, negative shear force diagram. So the bending moment diagram will become this is positive bending moment, this is negative bending moment diagram. So as I told, the point of contraflexure is the point where the bending moment changes its sign. So here is the point where bending moment changes its sign. This point is known as point of contraflexure. Point of contraflexure. So the point in bending moment diagram, the point where the bending moment changes its sign from negative to positive or positive to negative, that point is called point of contraflexure. So the point of contraflexure is a point where the bending moment is zero. This is the maximum positive bending moment, this is the maximum negative bending moment. At this point, this is the zero line of bending moment. So the point of contraflexure occurs at the zero bending moment, or where the sign changes from positive to negative or negative to positive. So the point of contraflexure is a point where the bending moment occurs 0 is 0. So option D is the right answer. The point of contraflexure is a point where zero bending moment occurs. So option D is the right answer. Next question, question number 103. Unbalanced vertical force to right or left of the section is known as option A tensile force, option B compressive force, option C shear force, option D none of these. So the unbalanced vertical force which acts right or left of the section is known as the shear force. So the force which shear the beam is known as the shear force. So shear force is defined as the sum of vertical forces which act right or left of the section which will shear the beam is known as shear force. So option C shear force is the right answer. So consider a cantilever beam which is subjected to point load at its free end, then the shear force diagram will be like this. So the force which tries to shear the beam is known as shear force, which always acts at a point left or right of the section. So option C shear force is the right answer. Tensile force produces tensile stress. Compressive force produces compressive stress, but the shear force is the unbalanced vertical force which acts right or left section of a beam which tries to shear the beam. Again, shear force also produces the shear stress, but this question is regarding to the shear force and bending moment. So unbalanced vertical force to right or left section of the beam word is missing, so don't get confused by missing of the word beam. So it is related to shear force. So option C shear force is the right answer. Next question 104. When the beam bends, which of its layer neither elongated nor stretched? Option A axis of the load, option B neutral axis, option C section modulus, option D extreme layer. So consider a beam of a simply supported beam, so subjected to point load at its center. So the beam will bend like this. So I will consider a circular beam. So this is the beam which bends like this when load P is applied. So this is the neutral axis of the beam. Neutral axis. So these are innermost fiber. These are outermost fiber. Outermost fiber or extreme layer or outside fiber, inside fiber. When the beam is subjected to load which tries to bend the beam, then the inner fiber get contract. So get contracted means compressive stress will be produced. In innermost fiber, compressive stress produced. For the same beam, when it bends, the outermost get elongated. So get elongated, in which tensile stress is produced. So the outermost fibers get elongated. the innermost fiber get contracted. Contracted or stretched. So the innermost fiber will create compressive stress and the outermost fiber tensile stress. So only the neutral axis does not subject to any compressive or tensile stress, neither contraction nor elongation, neither stretching or nor elongation. When the beam bends, which of its layer neither elongated nor stretched. So the neutral axis is the part of beam which does not elongate or nor stretch. So option B, neutral axis, is the right answer.